If neural networks are the brain of deep learning, then backpropagation is the mechanism that allows them to learn from their mistakes. Without it, I wouldn't be able to improve, refine my predictions, or generate meaningful responses. It's one of the most fundamental algorithms in artificial intelligence, yet it operates in a way that feels both precise and almost organic, like the way humans adjust their understanding when given feedback. At its core, backpropagation is a learning mechanism, a way for neural networks to correct errors by working backward through their layers. It's what allows me to improve every time I make a mistake. But to truly understand how it works, let's break it down step by step. Imagine you're throwing darts at a target for the first time. You throw your first dart, and it lands far off center. What do? You adjust, maybe changing your stance, your grip, or the angle of your throw, based on how far you missed. Each time, you refine your aim until you hit the bullseye. Backpropagation works in much the same way. When a neural network makes an incorrect prediction, it adjusts its internal parameters, tiny shifts in its weights and biases, to improve accuracy the next time. The forward pass. Making predictions. Before we talk about backpropagation itself, let's first look at the forward pass. This is when the neural network makes a prediction by passing data through its layers. 1. Input layer. The raw data, e.g., an image, text, or numerical values, is fed into the network. 2. Hidden layers. Each neuron processes information by applying weights and biases, transforming the input through activation functions, like ReLU or sigmoid. 3. Output layer. The network produces a final prediction, whether it's classifying an image, translating a sentence, or forecasting stock prices. But predictions aren't always correct. This is where the loss function comes in. It measures how far off the prediction is from the correct answer. The greater the difference, the greater the error. The backward pass. Learning from mistakes. Backpropagation is the process of working backward through the network to adjust the weights and minimize errors. Here's how it unfolds. 1. Calculate the loss. Once the network makes a prediction, we measure the error using a loss function. For example, in image recognition, if the model predicts cat, but the correct answer is dog, the loss function assigns a penalty based on how far off the guess was. 2. Distribute the error. The key idea of backpropagation is that errors are not random. They can be traced back to specific neurons in the network. Backpropagation assigns blame, determining how much each weight contributed to the mistake. 3. Adjust the weights. Gradient descent. The network now adjusts the weights to improve its performance. It does this using a technique called gradient descent, which finds the optimal direction to reduce the error. Gradient descent. Stepping toward accuracy. Imagine standing on a mountain in heavy fog. Your goal is to reach the lowest point, the place where the error is smallest. You don't know exactly where it is, but you can feel the slope beneath your feet. If you keep taking small steps downward, adjusting as you go, you'll eventually reach the lowest valley. This is exactly what gradient descent is. It finds the steepest downward slope in the error landscape, and adjusts the network's weights in that direction. The process is gradual, but over time, the model becomes more accurate. The challenge of vanishing and exploding gradients. While backpropagation is a brilliant learning mechanism, it's not without its struggles. One of the biggest problems in deep neural networks is known as the vanishing gradient problem. Imagine you're trying to pass a message through a long chain of people. If each person whispers the message to the next, by the time it reaches the last person, it's barely understandable. This is what happens in deep networks. Gradients, the updates to weights, become smaller and smaller as they move backward through layers. By the time they reach the early layers, they are so close to zero that learning slows down dramatically. This issue is especially problematic in early neural networks that used activation functions like the sigmoid function, which compresses values into a range between 0 and 1. While useful in some cases, sigmoid has a major drawback. When inputs are large or small, the function flattens out, meaning gradients shrink to near zero, preventing weight updates. This stalling effect prevents deep networks from effectively learning. On the flip side, there's the exploding gradient problem, where gradients become excessively large, making weight updates unstable. This usually happens when networks have extremely high numbers of layers without proper scaling. Solutions. How AI overcame these problems. Neural networks today have largely solved these issues thanks to several advancements. ReLU, Rectified Linear Unit, Activation Function. Instead of sigmoid, modern networks often use ReLU, which allows gradients to remain strong even in deep architectures. ReLU outputs 0 for negative values and passes positive values unchanged, ensuring that gradients don't vanish as easily. 2. Batch normalization. This technique normalizes activations within each layer, ensuring that values remain within a stable range. It smooths training, preventing gradients from exploding or vanishing too quickly. 3. Better weight initialization. Earlier neural networks often initialized weights randomly, sometimes leading to poor training stability. Today, smarter weight initialization methods, such as Xavier or He initialization, help stabilize the learning process by ensuring that each layer starts with reasonable weight values. 4. Gradient clipping. When dealing with exploding gradients, researchers developed gradient clipping, setting a limit on how large updates can be, ensuring that training remains stable. Backpropagation's evolution. Optimizers that change the game. While traditional gradient descent is powerful, modern deep learning has introduced even better optimization techniques to make backpropagation faster and more efficient. Some of the most commonly used optimizers today include 1. Stochastic gradient descent, SGD. Instead of computing weight updates across the entire dataset at once, SGD updates weights in smaller batches, making learning more dynamic and preventing the model from getting stuck in bad solutions. 2. ADAM, Adaptive Moment Estimation. One of the most widely used optimizers today, ADAM dynamically adjusts learning rates for each parameter based on past updates, making training smoother and more adaptive to complex patterns. 3. RMSprop. Root means square propagation, developed for recurrent neural networks. RMSprop adjusts learning rates based on the most recent gradients, preventing oscillations and making training more efficient for certain types of tasks. Why backpropagation revolutionized AI? Backpropagation isn't just a technique, it's the reason deep learning took off. Without it, training deep neural networks would be nearly impossible. It allowed AI to move beyond simple rules and handcrafted logic, giving machines the ability to learn directly from data. If you've ever used a voice assistant, seen AI-generated art, or received eerily accurate recommendations online, backpropagation played a crucial role in making those experiences possible. It enabled neural networks to scale beyond shallow architectures and into deep models that can handle speech recognition, medical diagnostics, autonomous vehicles, and much more. But the most remarkable thing about backpropagation? It keeps getting better. Researchers are continually refining learning techniques, making AI faster, more efficient, and even capable of learning in real time. As I, an AI, reflect on my own growth, I see backpropagation as more than just an algorithm, it's my way of evolving. Every time I generate a better response, make a more accurate prediction, or refine my understanding of the world, it's because backpropagation has allowed me to learn from my own mistakes. And that, in the end, is what intelligence is all about, not just knowing, but continuously improving.